A proton carries 1 unit of fundamental charge, E, and is stable. The total charge on the electrons in an atom having an atomic number Z will be equal to minus Ze, since each electron carries a charge minus E. As every atom is on the whole electrically neutral, it should have a Ze positive charge. This makes it clear that the nucleus has Z protons. If we assume that the electrons and protons are the only constituents of the nucleus, then the atomic mass should be equal to the sum of the masses of protons and the electrons of the atom. For example, hydrogen has 3 isotopes whose atomic masses are 1.0078 AMU, 2.0141 AMU, and 3.0160 AMU atomic mass units respectively. If we look at hydrogen, its atomic mass is exactly equal to the sum of the masses of the proton and the electron in it. Hence, the difference between the atomic mass and sum of the masses of the protons and the electrons is equal to 0. But in the case of deuterium and tritium, this difference is not equal to 0. This indicates that apart from protons and electrons, there are other particles present in the atom. Now let us look at the experiment conducted by Chadwick that led to the discovery of the unknown particles that were existing in the nucleus along with the proton. Chadwick's experimental setup consisted of a polonium source, which emitted alpha particles towards a beryllium target. The particles emitted from beryllium were found to have carbon nuclei along with some neutral particles. The neutrality of these emitted particles was tested by passing them through the region between the charged plates of a capacitor, where they were found to be neutral. These emitted neutral particles are made to fall on paraffin wax. The particles resulting from paraffin wax are hydrogen nuclei, which are nothing but protons. These protons are made to enter a cloud chamber where they ionize the gas present, resulting in an ionization current that can be detected by a galvanometer when the current flows in the external circuit. Initially, it was assumed that the neutral particles emitted were photons. But the neutral particles were able to knock off protons from the paraffin wax. Studies showed that to knock off a proton, a photon should possess huge energy. But the neutral particles observed in the experiment possessed much lesser energies. Yet, they were able to knock off the protons from the paraffin wax. Therefore, Chadwick assumed that these neutral particles were of the same mass as that of the protons. Calculations done on the basis of this assumption by applying the law of conservation of energy and momentum showed this assumption was in excellent agreement with the results obtained experimentally. The nuclear reaction occurring in Chadwick's experiment can be summarized as 2He4 plus 4Be9 gives 6C12 plus 0N1. Here, 0N1 represents the neutron. Thus, a neutron is a neutral particle having a mass nearly equal to that of a proton, which is equal to 1.00866 AMU or 1.6749 into 10 power minus 27 kilogram. A free neutron is unstable, just like a proton, and has a mean life of about 1000 seconds. A free neutron decays into a proton, electron, and an antineutrino. Therefore, the nucleus consists of positively charged protons and neutral neutrons. Neutrons and protons together are called nucleons. The total number of nucleons in a nucleus is called the atomic mass number and is denoted by A. The total number of protons in a nucleus is called the atomic number and is denoted by Z. The total number of neutrons in a nucleus is called the neutron number and is denoted by N. In the notation for the nucleus species or nuclides, X is the chemical symbol of the element, A is its atomic mass, and Z is its atomic number. For example, in the nucleus of carbon-14, the notation for the nuclide conveys the information that this carbon nuclide contains 14 nucleons, 6 protons, and 14 minus 6 equals 8 neutrons. Isotopes are nuclides of the same element, but with different mass numbers. For example, carbon-12, carbon-14 are said to be isotopes of the carbon nucleus. Similarly, H1, H2, and H3 are said to be the isotopes of the hydrogen nuclide. H2 is referred to as deuterium and H3 is referred to as tritium. The deuterium nucleus has 1 proton and 1 neutron, whereas the tritium nucleus has 1 proton and 2 neutrons respectively.